2 segunditos de retraso. Ya lo presioné. Going live. Yes, okay. I think we're live. Welcome back, everyone. Thank you for joining us for today's lawphysics colloquium, not webinar. My name is Alejandro, and I'm going to be your host. Today, we're presenting Protoplanet Express, a video game based on hydrodynamical simulations by Jorge Cuadra. Jorge earned a bachelor's in astronomy from Pontificia Universidad Católica de Chile and his PhD at the Max Planck Institute for Astrophysics in Garching, where he worked with professors Nayashkin and Sunyaev. He then moved as a research associate at the University of Colorado, and then he went to a joint position at the MPA, Max Planck Institute for Astrophysics, and the Shanghai Astronomical Observatory. Then he became an assistant professor at Pontificia Universidad Católica, again in Chile, and then he moved to Universidad Adolfo Ibáñez, where he is currently a full professor. Jorge's research has spanned over several topics and in very interesting topics. Fundamental, he has made an impact. But then the main topics are gas dynamics, massive black hole binaries, star formation, as well as, and that's what we're going to learn today a little bit, Protoplanetary Disks, which is, he's going to tell us about this nice application / game. We are delighted to have him here in lawphysics today. So remember, you can ask questions over email, through our YouTube channel or Twitter, and then the questions will be read at the end of the talk. Without further ado, we will turn it time to Jorge. Thanks for joining us.
Thank you very much for the invitation. Give me a minute to share the screen. I think it should be working now. So
we also see your notes, so you might want to switch the.
Okay. Let me try that again. What about now? Okay, this always happens. Somehow I cannot remember how to do it properly. So thank you again for the invitation. I'm going to present you a game we are developing together with engineering students from Universidad Adolfo Ibáñez in Viña del Mar, where I work, and also from Universidad Santa María in Valparaíso nearby, both here in Chile. And the game is about protoplanetary disks. So the idea is to present these objects to the general public in a fun way. So this is, of course, is an outreach tool. That's our intention at least. And we hope to develop it, to release it in the coming month or so. Let me start this presentation giving you some context on the process of planet formation and what protoplanetary disks are, how we observe them and how we model them. So I'm going to start then with this nice picture. This is an image of a star-forming region. So here you can see many young stars that are already born, but they are in this medium where there's still a lot of gas and dust. And you can see here the shape of the cloud, the shape of the nebula, how it's being sculpted, it's being shaped by the winds of the stars, by the radiation of the stars. So the gas is being pushed, it's being compressed. And because of the dust, the dust and the gas are mixed together. Because of that, it becomes opaque. We cannot really see through when we look at it with normal telescopes, with telescopes that collect optical light. And so if you look at this, I mean, it's a very nice image, but you cannot learn much what's going on here. So what people have done, astronomers have done, is to use other wavelengths. For example, if we switch to the infrared, we get a completely different view. So this is the same cloud, I'm switching back from optical to infrared. And as you can see, regions that are opaque, very dark in the optical, look bright in the infrared. So that's the gas and dust accumulated, and where you have dust at the right temperature, it radiates in the infrared, and you can see its structure. And as you can see, the gas is becoming filamentary, it's becoming clumpy, and this is the result of the gravity. The self-gravity of the gas is making it agglomerate, accrete, get denser, you know, and in those regions, stars will be formed. To understand, this is a very, I mean, one can of course write a couple of equations to describe this process in a spherical, making approximations of or assumptions that everything is spherical, isotropic, and so on. But of course, the problem is very complex, and the way it's mostly studied nowadays, it's with numerical simulations. This is a nice example by Matthew Bate, in which we see one of these clouds of gas collapsing due to its own self-gravity, becoming forming filaments, forming clumps, and you can see them already popping out and then moving. We see the stars forming within the cloud in the densest regions. This is kind of a large-scale view of a cloud that is, I don't know, tens, maybe hundreds of light years across, and which can form hundreds of stars, maybe. Now, if we zoom in a smaller region, in a region where maybe one or a few stars will form at most, we can imagine what's happening. And so I'm going to start with this very, schematic view. So there's a cloud, and the cloud is somewhat spherical, and for sure is going to have a little bit of rotation. It would be really weird that it didn't rotate at all. Well, that rotation has an important consequence. And because remember, this cloud is collapsing due to the gravity, due to its own gravity. So a particle of gas that is somewhere here along the rotation axis is going to feel an acceleration, is going to move towards the center, right? But a parcel of gas, which is in the perpendicular direction across on the midplane, let's say, of the cloud, is going to feel not only the gravitational attraction pulling it to the center, but also is going to feel the rotational support of the cloud. It's going to feel a centrifugal force, which is going to push it outward. And at other positions, there's going to be an intermediate situation. I mean, this is a long way of saying that a spherical cloud, because of the rotation it originally had, and it will become more and more important as the cloud compresses due to conservation of angular momentum. So that cloud will tend to flatten and form a disk. Now, the inner part of the disk is going to become hotter and denser, because that's where that's where the material is collapsing on, right? So it's going to accumulate most of the material, and that's where the star is going to form. So you basically keep on piling up gas until the density and the temperature are high enough to burn hydrogen to make thermonuclear fusion, and there's your star. That's how star formation occurs in one sentence. In the in the outer part of the disk, there's going to be a lot of gas still, and that gas is going to be hotter closer to the star, and it's going to be cooler further away. And in the hottest part, lighter materials, volatile materials, are going to be pushed, are going to be dispersed, are going to dissociate because of the temperature, and you're going to end up with a mostly denser material, right? Denser elements. And while in the outer parts, the volatile components will remain. And the material will then agglomerate, and you will end up with mostly rocky planetesimals in the inner part and icy planetesimals further out. This is what we nowadays identify as asteroids and comets, that they are still around in the solar system, some of them. And these planetesimals, of course, will agglomerate further, will grow by collisions, by merging with each other, and will end up creating the terrestrial planets and the giant planets. This basic picture has been around for many, many decades, and it was developed in the context of the solar system. Nowadays, we know reality is more complex. We have evidence that there are planetary systems which do not follow the same architecture of the solar system. They have, for instance, giant planets very close to the star. So more ingredients have been added to this basic picture, basically different physical processes that make the planets migrate, change their location. So a giant planet can move from the outer part where it formed to the inner part close to the star due to different dynamical processes. But anyway, this basic picture is a good first approximation to have in mind. It still works to understand how planetary systems form. So how do we see this? How do we observe this? This is what we could see like 20 or 25 years ago. These images show protoplanetary disks, how we could see them just like a dark circle or a dark ellipse with a star, something bright, which is the star in the center. So not much detail. Nowadays, we have a very different picture thanks to new observatories. And the one I think it has been most important is ALMA, the Atacama Large Millimeter and Submillimeter Array. This is in the Atacama Desert in Chile, and this observatory has 60-something antennas, and they work together as an interferometer, and they can move. At least some of the antennas can move, and depending on how far apart they are, since they are working together, they give you more resolution. And that's great, because that means that you can observe very fine detail. You can see very small details in the structure of the object you're observing. Also, they work at a frequency that they detect light, electromagnetic waves of the frequency in which protoplanetary disks emit most strongly. Temperatures of a few tens of Kelvin, right? the dust at those temperatures emitting the wavelength that is captured by this array. So, and let me show you how the disks look now. So this is it looks like a computer simulation. The first time I saw it 8 years ago, I think, I couldn't believe it was a real picture. But this is how we observe protoplanetary disks right now. And as you can see, there's a lot of structure. The one I'm showing you now is called HL tau. And you can see these bright rings, which are separated by dark rings. So there's this structure that was actually expected. As I will show you in a minute, this is the result of, we think, this is the result of planets forming in the disk. Although it was a surprise that a star as young as this one showed already this structure. And other disks do not show this ring and gap structure, rather show asymmetries. For instance, here you see this bright part over here on the top right, and this bright part here on the bottom right, closer in. We see a large cavity, a dark empty region, and something like a ring and maybe a spiral arm. So there's more stuff, more processes going on. And these are two examples, but actually nowadays there's a few dozens that have been observed in this detail. And yeah, as you can see, there's gaps, rings, spirals, and asymmetries of different kinds. So how do we understand this? How do we interpret these observations? A possible explanation is that there are planets or binary companions driving this structure, creating this structure. The case on the left, what I'm showing now are snapshots from computer simulations, hydrodynamical simulations, I should mention that. The example on the left is a simulation of a system in which we know there's a binary star in the center. We have actually observed that there are two stars, we know for sure. And if we have this binary inside the disk, we see that a large cavity is created. Basically, the gas cannot have stable orbits very close to the binary. So that's how the cavity is created. We see that there are spiral arms that take material from the disk onto the stars. We see that same process makes the inner rim of the disk not uniform, also asymmetric. This part here on the left is brighter than the part on the right, and so on. The same happens if you have a planet. Rather than creating like a large cavity, there's a narrower feature which we typically call gap, and this gap is because of the gravitational interaction, torques between the planet and the material in the disk. If the planet is massive enough, say massive as Saturn or Jupiter, it will likely open up a gap in the planet and also drive spirals and so on. This here is a particular example I want to highlight. This is work led by Pedro Poblete. And in this case, we had to put both a binary star in the center and a planet further out to reproduce the observations of the system of HD 169142. So that's a particular disk we observe on the sky, and so this model is tuned to reproduce what's happening there. And we had to put both the binary and the planet in order to create this ring here, this other ring closer in, to make the ring clampy and so on. I will discuss it a bit more in a bit more detail later. And I should point out that current simulations have the ability to follow both the gas and the dust separately. So it's not one fluid, but two fluids that we are modeling at the same time. And this is important because the gas and the dust have a different behavior. As you can see in the images, the gas tends to make spirals more easily. It's also overall smoother, while the dust tends to give you sharper features. So we see these rings, you know, narrow rings, also these arcs here. And I'm going to explain you why that happens. If you think of a gaseous disk rotating around a star, you could think that the velocity of the gas is simply given by the gravitational potential of the central star. But actually, the pressure gradient becomes important. There's a pressure support. Typically, the pressure is higher in the inner part of the disk than in the outer part of the disk, and that gradient tends to push the gas out. So as a result, the gas rotates around the star a bit slower than a planet would do. So that's what we call sub-Keplerian. If you have very small dust grains, like the ones that are typically found in the interstellar medium, micrometer sized and smaller, that dust is very well coupled to the gas. It just flows with the gas. So that dust is fine, follows the gas, it has the same distribution, more or less. However, as the dust agglomerates, accumulates, and the grains grow, the dust becomes well, heavier, we would think, right? And it's not so well coupled to the gas anymore. So it will tend, the larger dust grains, millimeter sized and higher, it will tend to rotate at the Keplerian speed. So just due to gravity. But as it does it, as it rotates or tries to rotate at that velocity, it feels friction. It feels a headwind with the gas, from the gas, that is rotating more slowly. And as a result, it loses energy. So the dust, in particular the larger dust grains, lose energy because of this friction and tend to drift inward towards the star. And in principle, you could lose a lot of the dust in the disk, and it just falls onto the star and is wasted for the planet formation process. And so one way to, one reason for this not to happen is, well, if you have a planet already, what happens if you have a planet? If you have a planet, the pressure profile of the disk, this is a schematic view of the pressure as a function of radius along the disk. The pressure profile of the disk changes. And you have a region in which the pressure gradient actually becomes 0. There's no contribution from the pressure gradient. So in this region, which is just outside the planet orbit, just outside the planetary gap, for example, the dust will accumulate. The dust will come from the outside, it will be falling, and then it gets to this pressure maximum location and accumulates there. So that's why dust, and that's captured in the simulations, that's prescribed in the simulations. So that's why the dust forms these sharper features than the gas. And this is quite important to reproduce the simulations. Here I'm showing you how it looks to reproduce the observations. This is how we simulate it, and this is the same system how we observe it. So if we observe the very small dust grains, which trace the gas distribution, we see spirals. That it's not a very clear view, but this more or less shows you what we saw in the gas simulation, while the millimeter observation, sub-millimeter observation, show you the dust. Show you what we simulated as dust. All right, so after that came longer than I expected, but after that introduction, I'm going to go to the video game. Okay, so we wanted to use the numerical simulations, the models, to let the general public, to let people interact with protoplanetary disks in a fun way. So the ALMA images and other images produced by large observatories are great, of course, are very inspiring, but they are just an image. It's something you can see, you can enjoy, but you cannot typically play with. The numerical models we produce to explain the observations, to understand the evolution of these systems. On the other hand, we can interact with them, we can move them around, we can use better, I think. So we thought, well, maybe a game is the way to do it. And we wanted to use real simulations, published simulations of specific protoplanetary systems. So we can tell people, okay, this is a model of that system in the sky. And we show them pictures, a observed picture, and you can play with that object that you see on the sky. You can play with that in the computer. So we looked into our archives and we asked our kind collaborators to give us snapshots from their models, and we concentrated on smooth particle hydrodynamics models. Why smooth particle hydrodynamics, SPH? Because in SPH, the gas and the dust are modeled with a collection of particles. So it is relatively straightforward to take a snapshot and use it in a different platform. So if you have another kind of simulation, it's not necessarily obvious how to translate that and put it somewhere else. If you have a grid, for example, especially if it's a grid with non-uniform resolution. But with SPH, it's more or less trivial to move it from one platform to another. We use a Blender to design the spaceship, which I'll show you in a minute, and we use Unity to build the game. Blender and Unity, perhaps you've never heard of them, but they are standard tools in the video game industry. And so we use them because we wanted to do something that looks like a real video game. Actually, these are not images of our video game, but this is what we aimed for, right? This is the kind of this was our inspiration. We wanted to go in this direction. So we didn't want to create simply an encyclopedic app. We wanted to make a game. And this is how our spaceship looks like. So this is, you are inside the ship, going to the cabin, sit down, take the controls, and this is when you start. That's the Earth. So that's when you start from your base and take, there's a non-physical hyperspace jump to reach another system. This is a snapshot of us working with Unity to, here we were deciding which colors to use for the different particles, how to illuminate them. It's interesting that, I mean, we don't do ray tracing or radiative transfer in a strict, in a physical sense, in a physically correct way. That's what I meant. But actually, you can put light sources in the game, which work. We have stars, and the particles will have some sort of transparency or opacity, and they will reflect an albedo. They will reflect light. So in the end, it actually looks quite all right, and it works to give you a good idea of how physically it would look. This is a snapshot from the game again. Here we are in the central part of the ship, looking out the window, and here's a protoplanetary disk surrounding the star. Now I'm going to show you the different systems we've included in the game, how they look in real life with observatories, with telescope observations, how they were modeled, and how they look inside the game. The first system is the STAU. This is the first one you encounter in the game because it's the simplest. It's only one gap here, which is modeled with one planet. So this is a simulation done by Benedetta Veronesi and collaborators. And so it's a gaseous disk with a central star that is not seen here, and a planet here. You can see how the planet drives these spiral arms, both inward and outward. And you can see in the dust distribution, this is dust of 0.5 millimeter. You can see how the dust creates these two rings. And this is how it looks in the game. So here you are in the cabin, and you see the central star, the inner ring, the outer ring, and the planet. You can see there's both orange and green particles. The green particles are the gas, and the orange particles are the dust. Something nice, I think we included in the game is that you have to go and discover features, interesting features. And so you learn something about the physical processes happening here. So for example, here, the player just discovered the spiral pattern, the spiral wake produced by the planet, and you get an avatar that gives you an explanation. The gravity of the planet is producing a spiral wake that is especially observable in the gas. And the character that gives you that explanation is based on the main developer of each model. So in this case, we have Benedetta Veronesi herself telling us this information. The next system is PDS-70. This is a system in which we observe two planets. So there's a star here, and one planet is clearly visible in this image. So that's modeled with star and two planets. This is the gas distribution from the simulation. And this is the dust distribution from the simulation. And this system in particular is very interesting because we observe the material being captured by the planet. So there's, and you can see it here in the model. That's reproduced in the model. So there's a spiral that brings material from the outer disk onto the planet, where it creates a circumplanetary disk where moons could be forming. This is how it looks in the game. Here we have Claudia Tocci. She is the main developer of this model, telling us how, what I just told you, right? The material comes from the outer disk onto the planet where it forms a circumplanetary disk. The next system is HR 8799. In this case, there's a star surrounded by 4 planets. This system is well known because we have observed it for, well, maybe 20 years now, and we see the planets going around the star. We know for sure there are 4 planets, and further out, there's a so-called debris disk. A debris disk is left over from the protoplanetary disk phase. So it only has dust, the gas already dissipated. And in this case, we didn't have a simulation as such available, but we had parametric models that fit both the observations and the dynamics of the system. So we know this is dynamically stable, right? Developed by Virginie Paramas, the model, right? And she kindly turned this model into a particle distribution that we could put in the game. Here you are close to the star, which is here. You see 2 planets in this view. I mean, it's me saying it, but it's really beautiful how the planets have their texture. They look like green versions of Jupiter, and also they show only the part that is, you can only see the part of the planet that is illuminated by the star. So they show faces as we see on the moon or on Venus with a telescope. And yeah, here Virginie is telling us something about one of the planets. And notice that the disk is only orange. There's only dust. There's another system here in which we have a binary star. Binary stars are actually quite common. More than half of the stars in the galaxy are in binaries or multiple systems. And this is a young binary star that is still surrounded by the disk. And as you can see here, the disk which, I mean, it doesn't show up great in this visualization, but the disk is brighter on one side than on the other. And this can be explained by, this is reproduced in the numerical simulations because the dust kind of gets captured in a vortex here, in a banana-shaped vortex, which is formed by the interaction between the spiral wakes produced by the binary motion with the outer, with the outer disk. So the gas, smoother spirals, the dust, you have sharper features, and in this case, this vortex. And this is how it looks in the system. And here's Enrico Ragusa, who developed this model, telling us how binaries are common in the galaxy. HD 1430 something, HD 1430-06 is a disk that has like two parts and this very bright feature here. And this can be explained by an inner binary and a planet a bit further out, with the inner binary inclined with respect to the disk. So this is the gas on the left, the dust on the right. The top panels show a face-on view of the disk, and this is an edge-on view. And yeah, the fact that the binary is inclined makes the inner disk get inclined, and this produces this reflection, which gives you this very strong asymmetry of the system. So you have scattering of the light, of the stellar light on this side of on the closer side of the disk that makes it look brighter. And this is Julia Balavio showing us her model of the system, showing us in particular the inclined disk. And here you can clearly, nicely see the planet, its spiral wake, and so on. In the last couple minutes, I'm going to show you a bit more of the game. This is the final stage, where you go to the system model by Pedro Poblete, the one I showed you the simulation at the beginning. Here you can see how you can turn on and off the dust and the gas if you want to study in particular one feature. And you have different objectives in each stage of the game. So different things you need to go and discover. And I think the first one there was the clumpy ring. So you go with your ship and discover or find the ring. And Pedro tell you that this has a ring of dust which is non-uniform, something like that. And then you discover that there's another outer ring and a gap. You can check what else you need to find. There's a planet you need to find. There's the planet. And Pedro tell you that the planet is responsible for the creation of the gap and the ring. There we went through the spiral wake produced by the planet. And here you see the binary companion to the central star. And notice that it's like further away, it's out of the plane. And I think this really illustrates how relevant is that we have at least for some models, it is very relevant that we have the three-dimensional structure, right? And you can look at it from different angles and learn something. You can work on the ship. You can see actual images of this object, how it looks from Earth. You can read more information. And in the center of this room, there's a hologram which you can interact with, and you can like review the different features you've discovered. Once you discover them in space, they appear here in the hologram, and you can read what they are again and look at them in context and so on. And right, I think that's probably enough of the preview now. So just let me finish telling you that we are planning to release a beta version very soon. That's hopefully in a couple of weeks, maybe a month. The idea is that this beta version is released to people working on the field, people who have seen this presentation. So I will be happy to share it with the organizers here, so they can put it in the on the social media of this webinar series. And yeah, then we want to make the game look more professional, add an introduction, tutorial, have credits, you know, all that's needed for a proper public release. And then for the future, there's several possibilities. We would like to make it look even nicer, to have a smoother distribution. So for that, it would be good to use Sph interpolation. So the same technique that was used to create the images from the simulations I showed you through the talk, in principle can be used in real time in the game, and it would be great if that can be implemented. And we can add more systems, we can have more snapshots, so you see the evolution of each system. And a very exciting possibility is to turn this into a virtual reality application. So rather than playing on the screen, you put some goggles on and you fly through the system in a even more immersive way. With that, I finish, and thank you very much for your attention.
Awesome. Thank you, Jorge. This is amazing. I want to play with it. So please let us know when it goes out. I don't see any questions here on the YouTube channel. Let me check this Slack. And in the meantime, if someone here, one of the lawphysics coordinators, wants to ask a question, please go ahead. Let me start. I have several questions, and in particular, just for pedagogical. Okay, I can never say this word in English. Pedagogical reasons, or just for like teaching. How steep is the learning curve for students? Like, of all these tools, and what's the background they need in case someone wants to contribute?
Oh yeah, that's a good question.
For the
These
tool,
are actually
Blender and Unity, the things you said, like how hard it is to start learning those tools. I'm talking about the development of the game.
Yeah, that's a good question. Actually, that's the students who are involved or have been involved either were informatics students or were using already these tools as a hobby. So yeah, I don't have a good answer then for your question, because none of them started from scratch.
I see. And so just out of curiosity, I don't want to put you on the spotlight, but let's say, I mean, you know the tools right now. So, I mean, you are as an astrophysicist, was it too hard for you to jump to start using that? Or is just your students making them?
It's mostly the students. So I have sat with them and look at them, and actually I'm better at a few things. I'm better than them, like using command line to do grep, that kind of thing.
Okay.
But with Unity and Blender, it's all their work. They sit down and do stuff, and I understand what's going on, but I haven't really done it on my own.
I see. And those Blender and Unity are open source tools?
They are free. I'm not sure they're open source.
Okay.
I think Unity, it's not for sure. Like you can use it for free as a student or for academic reasons, but it's not open source.
Okay, and then just also like maybe a detail. So in principle, people are giving you their simulations and your simulations, and then and you put that into your game. So my question is, like, I can imagine those simulations are super heavy. But then once you put in the game, I can imagine they are going to be more heavy wise. So how does that interaction work with the data, or you then make some post processing or something like that?
Yeah, it's been a bit of a challenge. I mean, each simulation has around 1 million particles.
Yes.
So it's a lot, but it's not a huge number nowadays. But if you simply, in a brute force way, load the particles in the game, the game takes forever to load. Like each time you run it was several minutes to load the particle data. So what we had to do was to create like an object with all the particles. So you do that once, and then it's compiled in the, it is ready in the compiled version of the game. So when you run it, it loads quickly.
Okay.
So we've had challenges because of the volume of data, but yeah, and I think that's going to be a challenge for what I put here, use Sph interpolation. I think that's, I'm not sure if it's going to be feasible, but
great.
But yeah, maybe.
Jorge, maybe I missed this, but this is a computer game, right? Video game, or is
yes?
Or okay. Are they also any plans? I remember, I forgot. There's a professor in Toronto that he does planets, I think, also, or something like that. Like you can use an iPhone or a phone, and then you can move around. That will be, because I see the VR version is in your plans, but maybe having just the phone that you can move around might be, I don't know if it's cheaper, easier, but maybe it's nicer for the public, because in the VR you might need the full equipment. And I believe nowadays people might have more a phone than the VR. So maybe that's for sure. Maybe
that's definitely a possibility. We actually have experience on that. We created with a former postdoc, with Christopher Russell, we created a visualization of galactic center simulations before, and we did that in VR. So we have versions for what is it? I forget the name. But one of the goggles that you can buy, but also a version that you can watch with the phone on YouTube. Okay. However, the problem with that is that it was too complex. It was hard for the user to know what was going on. I think this one has the advantage that a disk is, even though I say, oh, we want to show the structure, these are complex things, but still, it's more or less a disk around a star. People can more easily grasp what's going on.
Okay, I see. I don't want to take control of all the questions. Is there any other? But Joel?
So yeah, this thing of the work is fantastic. So really cool. So how do you plan to do this time evolution, right? Because you cannot play the game and solve the Navier-Stokes equations at the same time. So how do you How do you plan to do this?
Oh, I mean, you have the simulation run in advance, right? It would be loading several snapshots rather than only one.
And size-wise, regarding how big the game is in this sense, how does that change?
You would make it much heavier, I guess. So now the executables are like 1.5 gigabytes with the 6 levels. So yeah, it would make it, we would have to think of a way of compressing the data somehow, losing information, right? So maybe have lower resolution, or maybe only letting the inner part evolve, because obviously the inner part evolves faster. So yeah, we would have to do something smart. Brute force, I don't think it will work.
Right. And is there a bad guy in the game? Is there a Darth Vader in the game?
No, so far it's a very
so what's the
very
story
naive game.
in the game?
Just explore.
Okay, so it's like a Star Trek kind of story.
Yeah, without the Klingons.
All right.
Jorge, I have another question. Like, if people want to contribute, are you guys willing to allow contributions and then to make the game more modular, or like how is this design or plan to be released?
Well, to be very honest, we don't have a really good we don't have a plan. So we want to have a beta version out. And then we want to see how to move forward. So I think an obvious way to let people contribute would be to have researchers give us more models, right? Give us more stages. And so and that could work in different ways. We could let people simply give us a snapshot and then we transform it, or we could publish the scripts to go from one format to the other. We haven't really thought it through. We work hard on this during our summer, so January and February here in Chile, and because we had free time, right? But we have to look how to move forward with this, how to make it. Maybe we need a company to. I don't want to make money, but let professionals take care of it. I don't know.
Good. I see a question in the YouTube channel by Ayush Gautam. I'm sorry if I did not pronounce that correctly. Will you visualize the dynamics of binaries in the time evolution of disks around them?
Well, I mean, ideally, yes. So far, that's not implemented. So far, it's a fixed snapshot. So you go to the system and you move with your ship, but the system is static. The simulations do show the binary moving and do show the gas moving in response to the changing gravitational potential and so on. And in principle, it is possible to do it, but whether it's feasible, I'm not sure, because as well asked or pointed out, that's going to be very data heavy.
Good. I see someone also on the YouTube channel wrote that there are some resources from Stephen Wolfram about turbulence. So if someone is interested about that, I see. Let me see. Is there any other question that am I missing? I think we're doing great on time. We still have a minute or so.
I have a question.
Yes, please go ahead.
No, yeah, very nice the game, Jorge. So I was wondering, I mean, did you choose Unity? I mean, as far as I remember, Unity has the ability to have kind of physical engine to be to be able to simulate particles within the framework of Unity, as far as I know. So, but since you were saying that many of the stuff are very heavy, I don't know if it is just the choices of Unity and Blender is just because of the student know how to use it, or we were the best tool. I mean, I was wondering because there are these games that are kind of first-person shooters that they are very heavy and they do the ray tracing and everything. If you have considered maybe to also to include other type of engine for the visualization, for the to do the ray tracing for you, and you don't have to worry about the ray tracing, and to have better graphics. And the second question, just to add, in this version or in the beta version, do you need? I mean, the person that will play needs to have a I don't know, good enough graphical card, like a GPU acceleration, or it's just CPU? I mean, the hard work is made by the CPU only.
Yeah, so to answer the second question first, you don't need a GPU, but you need a relatively good computer. So I'm using my laptop and it works fine, but if I try it on my 5-year-old laptop, my laptop that is 5 years old, no, then you cannot run it properly. So that's part of the when we do the more professional release, we want to have it benchmarked in different computers. So to let people know these are required system requirements, and this is recommended, and so on. Now, your first question. So the candid answer is that it was the choice of the students. They said Unity and Blender, and I let them. I mean, they knew what they were doing. But yeah, it's an interesting point that Unity, in principle, you can run a simulation in Unity. You can put gravity. You can, I think, you can even put. Is it in Unity or in Blender? I'm not sure. But in principle, you can run an SPH simulation within the game. So maybe a way forward would be to take a snapshot from a proper simulation, put it in the game, and then let it evolve further using the Unity tools. So at least you could have it rotate due to gravity easily in real time by the GPU rather than having it preloaded. So that's a possibility, but yeah, we haven't tested it at all.
Okay, thank you very much. Thank you for everybody that joined us today. Our holidays are over, so lawphysics webinars will be starting, I guess, in 2 weeks will be the next one. And if not, please check our calendar. We will have, again, as usual, very, very nice speakers and talks for the rest of the season. So thank you very much, Jorge, for this very nice colloquium. And let us know when the game is out. We will definitely make it advertised. So thanks for joining us. Okay.